Hi everyone, in this tutorial I'm going to show you how to export your visual effects from Max to Maya. We'll see three methods. The first one with the native Maya Alembic importer, the second one with Bifrost, and the third one with USD. Here I'll be using Max and Maya 2026, but you can do it with previous versions. I'll also use Bifrost 2.14 and Arnold 5.5, but again it should not be a problem with older versions. The most important thing to have is TyFlow. You can use the free version, but make sure to use the version 1.128 or above. Let's get started. In Max, I've got a very basic TyFlow particle system, and to export it, we can simply use an export particles operator. The first thing to do here is to set its mode to Alembic mesh, and under the Alembic properties, make sure to set wall coordinates as Y up, which correspond to Maya. There are a lot of different options, but for now you can leave them like that and simply define a path for your Alembic file, then click on Generate Alembic File and switch to Maya. In Maya you can load an Alembic through different ways, but here I'm going to simply drag and drop the file directly into the viewport. The animation looks good so far. We can see that each particle has been imported as a separate object. Now let's add a light and take a look at the render. Overall it looks fine, but some of the cubes seem to have strange normals. Select one of them and unlock its normals to see how it behaves. You might need to refresh the scene and scrub through the timeline to update the render view correctly. Now we can see that this cube is displaying properly. You can do the same for the other cubes, just select them and unlock their normals as well. This works fine if you only have a few objects, but a better approach is to fix the issue before exporting. Let's go back to 3ds Max and open the TyFlow setup. Since we only want to fix the cubes, we need to identify their index in the shape operator. To do that, save the shape index as a custom float and visualize it using the display data operator. In our case, the cubes have an index of 0. Now add a smooth operator below the shape operator and use a filter based on the custom float value so that only the cubes are affected. Once that's done, export the particles again and import them back into Maya. As you can see, the cube normals are now properly fixed. In the Arnold render settings, enable motion blur. Since each particle was exported as a unique object with its own transform, Arnold has no trouble calculating motion blur. Now let's go back into Max and try exporting our particles with color. Start by adding a vertex color operator and set the hue variation to 100% so that each particle gets a distinct color. Save this color information to a map channel of your choice. Here I'm using map channel 5 to preview the colors directly in the viewport. Enable that channel in the display operator. Then apply a material using a vertex color texture and set it to the same map channel. Max viewport will only display an approximation of the colors. You won't see any blue colors because the vertex color is baked in a 2D map made of red and green. If you want to see the real colors, you can either render the particles or switch the display mode in TyFlow to something like sprites or dots. Next, let's configure the export particles operator to include the vertex colors. First, make sure the map channels are exported as color, since Maya expects RGB vectors. Then set the channel type to raw per vertex data, which is also required for Maya compatibility. Lastly, enable no spaces in property names. This ensures the attribute name is formatted correctly for Arnold shaders. Now export the Alembic and open it in Maya. You should already see some colors in the viewport. When you select an object, the color set editor will show the embedded map channel. Open the Hypershade and create a basic material. Add an AI user data color node and connect it to the shader's base color input. Copy and paste the name of your map channel into the AI user data colors attribute field, then assign the material to your particles. At this point, your objects might still appear black in the render. That's because Arnold doesn't read Vertex colors by default. To fix that, go to the Arnold tab in the Attribute Editor and enable Export Vertex Color. Render again, and colors should now appear correctly. If you only have a few objects, you can do this setup manually. But for larger numbers, use the Attribute Spreadsheet tool. Select all your objects. In the Arnold tab, find the Vertex color setting. Select the entire column and switch it from off to on. Re-render and you should see the colors. However, the teapots seem to have a problem, so let's head back to Max and investigate. Try adding a tie mesh repair modifier to the teapot. This reveals some mesh issues. Re-export the Alembic and reload it in Maya. This time the viewport displays the colors correctly. Don't forget to reapply the material and enable Export Vertex Color again. Now everything should render as expected. If you see some objects being oddly stretched, it probably means that Maya and the Alembic file have different FPS settings. Double check that both Max and Maya are using the same FPS settings. Now let's take a look at how to export a soft body simulation. Unlike rigid bodies, cloth pieces aren't treated as individual particles. Instead, they get exported as a single combined mesh. Start by adding an export particles operator and set the mode to Alembic mesh. You can deactivate the particle export, since we're only interested in exporting the cloth. Export the Alembic and import it into Maya. As expected, you'll see just one combined object in Maya. While the geometry displays correctly, motion blur doesn't work. That's because the vertex count changes over time, which Arnold can't handle for motion blur. To fix this, go back to Max and add a mapping operator in the second event. Set its mode to mapping by velocity and its timing to continuous. Choose a map channel, then go to the Export Particles operator and configure it, like we did earlier, to make it compatible with Maya. Since we are exporting velocity, we also need to convert the coordinate system, otherwise the Y and the axis will be flipped. Once done, bring the Alembic file into Maya and check the color set editor to verify the velocity map was exported. Now in the Arnold tab of the object's attributes, switch the motion vector source to use the map channel instead. Render again, and you should now get correct motion blur. Let's go a step further and assign a unique color to each piece of cloth. Because everything gets merged into one mesh, you'll need to assign the color before the particles are turned into cloth. To do this, add a mapping operator in the first event, set it to absolute value and choose a value of 1 with 100% variation. This gives you a random value between 0 and 1. Pick a different map channel and in the Export Particles operator, add this channel to the raw per vertex data field. Note, Max allows up to 99 map channels, but Alembic only supports 14. So if you're exporting to Alembic, avoid using any channel above 14, they simply won't transfer. Now, when you import the result into Maya, the color set editor should show 2 map channels. You can recreate a shader, just like we did with the rigid bodies. At this point, the render will only show variations of red because the mapping only affects the X component, which maps to R in RGB. The G and B channels are still 0. So instead of using this value directly in the base color, let's use it as a mask, create an AI ramp node and set its type to input. Connect the red channel from the AI user data color node to the ramp's input. Then connect the ramp output to the shader's base color. Now you'll see a gradient from black to white, and of course you can customize the ramp to use any colors you want. Now let's see how to export regular objects with color data. Let's demonstrate this with a simple sphere that has a slice animation. Suppose I want to create a border mask for use in a future shader. I can apply a tie select modifier and save the selection to a map channel. Now here's something important. The native Alembic exporter in Max doesn't support exporting multiple map channels as color data. However, according to the documentation, map channel 0 is always interpreted as vertex color. This is the only channel that Max will export as color data, which Maya can natively read. In Maya, we can see the vertex color was exported correctly. Max will triangulate any objects that belong to the editable mesh geometry class. If you want to avoid your mesh being triangulated during export, just convert it to a poly object. A quick way to do that is by adding a poly select modifier before the export. Now, if you want to export multiple channels, you'll need to use tie flow. Add another tie select modifier, this time set to random mode, and save it to a different map channel. This will be our second mask. Now let's make things more dynamic by adding animated noise. To compute the velocity, add a tie vertex velocity modifier. Enable velocity display in the viewport to check if it's working. If you see a warning about changing topology, that means the velocity can't be computed accurately. To fix it, switch the mode to proximity. That should solve the problem. Once it's working, save the result to a map channel, and again, remember, don't go above channel 14 or it won't export properly. Next, create a tie flow system and add an export particles operator. Pick the object into the additional geometry list. Then follow the same setup as in previous examples to ensure Maya compatibility. And don't forget to convert the velocity coordinates just like before. After importing the Alembic into Maya, the color set editor confirms that all 3 map channels have been exported successfully. Keep in mind, exporting velocity data can significantly increase the Alembic file size. Another way to export a mask is by baking it into a bitmap. First, let's simplify the setup. Disable the noise operator and keep only the first tieselect modifier. Then apply a vertex color shader to the object, using the map channel associated with the remaining tieselect. Personally, I like to plug it into the emission slot instead of the base color. It gives a cleaner result, and we don't need to place any lights in the scene to see the mask clearly. Now open the Bake to Texture window. Select your object and add an emissive map to the baking queue. Set the UV channel to 1. That might seem a bit counterintuitive, but here's what's happening. The Vertex color shader is already reading from the correct map channel and then displaying it through UV channel 1, which is what the baker uses. Bake the result, you'll get a proper black and white mask. Open the output folder to preview the generated file. Next, let's render this out as an animation. In the render setup, define your desired frame range, then rebake. Now it'll output a full image sequence. Once that's done, export the geometry as Alembic. Since the mask is now baked into textures, there's no need to export it as a map channel anymore. Import the Alembic file into Maya. If you see odd colors in the viewport, don't worry. Max may have assigned random shading groups, but that won't affect your result. If you open the color set editor, you will notice there are no map channels anymore, which is exactly what we want. Now create a new shader and assign it to the object. Add a file texture node and load the PNG sequence you just baked. Make sure to enable Use Image Sequence in the file node settings, then connect the texture to the shader's base color input. To preview the result in the viewport, enable the Texture Display mode, and if needed, make sure your FPS settings match the original scene so the sequence syncs correctly. Now let's go a bit further and see how to export multiple masks into a single bitmap. Start by reactivating the second tieselect modifier and add a third one as well. Each of them will save their data into a different color channel. For this example, I'm using object surface area as a selection method for the new tieselect, but of course you can use any logic that fits your needs. This is just for demonstration. To help analyze the geometry more precisely, I'm using a tool called GeoInspector Pro. It lets you inspect your object's data directly in the viewport, and you can get it on my Gumroad if you're interested. Once your selections are set up, go to the material editor. Duplicate the vertex color node twice, so you have 3 in total. Then create a component vector node and connect each vertex color node to one of its inputs. Connect the output of the component vector to your shader's emission slot or base color if you prefer. Now go back to the Bake to Texture window. Set the output format to full float E XR. This is important to preserve the precision across all 3 color channels. Then bake the texture. In Maya, load the EXR sequence into a file node. Don't forget to set the color space to raw to avoid unwanted color corrections. Now you can access each mask individually through the red, green and blue channels of the texture. When exporting particles as regular objects, Tyflow will often instance them automatically. This means that any modification you make to one object will be replicated across all identical instances. It's a very efficient and optimized way to work, especially when dealing with large numbers of objects, since it significantly reduces memory usage and improves performance. If you export your scene as Alembic, Max gives you the option to preserve these instances. So when you re-import the Alembic file back into 3ds Max, the instancing is maintained. Everything stays lightweight and optimized. Unfortunately, this doesn't work in Maya. Maya does not preserve Alembic instances. When importing the same file, it will treat each object as a fully unique mesh, even if they were originally instanced. Exporting a large number of particles into Maya can be challenging. In that case, a more efficient approach is to export only the particle points and then rebuild the instancing system directly in Bifrost. Start by adding an export particles operator in Tyflow and set its mode to Alembic point cloud. To make things easier in Maya, use the Bifrost preset. It'll name all the attributes correctly. Make sure to enable custom float exports too, since we'll need the shape index attribute to recreate the instancing. Export your Alembic file. In Maya, open the Bifrost graph editor and create a new graph. Start by creating a read Alembic node and load your Alembic file into it. Set the correct frame rate, and since this is an animated file, you'll also need to feed it a frame input. Add a time node and connect its frame output to the frame input of the Alembic node. Then connect the Alembic node's output to the graph output. You should now see the particles appear in the viewport. If you right-click on the connections, you can inspect the attributes, useful for debugging. In our case, we exported 20,000 particles, but the data browser shows only around 6,000. This usually means there's a mismatch between the Alembic file and Maya's FPS settings. Once you correct that, the correct particle count should appear. To better visualize the particles, add a point scope node. You can enable arrows to verify that the velocity attribute was correctly exported. Now let's take a look at the shape list in Max. We've got 3 instances: a cube, a geosphere, and a teapot. We can easily recreate the cube and geosphere directly in Maya, but for the teapot we'll need to export the geometry. Back in Maya, select your objects in the exact same order as they appear in the Tyflow shape operator, cube, geosphere, teapot. Then middle-click and drag them into the Bifrost graph. This creates a node containing a list of the 3 objects ready for instancing. Now it's time to instance the geometry onto the particles. Start by adding a Create Instances node in Bifrost. If you try to directly connect your Alembic points to it, you'll get an error. This is because the geometry needs to be merged before being passed to the instancer. To fix this, insert a Merge Geometry node between the Read Alembic node and Create Instances node. Next, connect the list of objects, the cube, sphere, and teapot, to the instance geometry's input. Since we previously connected a point scope node, the output node is still expecting point data instead of instances. To fix that, you'll need to recreate the output port to match the new data type. At this point, your objects should appear instance onto the points. However, you'll notice that the distribution is completely random. All shapes are mixed across the particles, which is not what we want. Remember, we exported a shape index from TypeFlow, stored as a custom float attribute. We'll use it to reassign the correct shape to each point. Add a getGeoProperty node and connect it to the merge geometry. In the property name, type the name of the shape index attribute. You can confirm it in the data browser. You should now see values ranging from 0 to 2, assuming you had 3 shapes, cube, sphere, teapot, which correspond to the correct index for each shape. Since the create instances node expects integer indices, add a convert node to change the float values to integers. Now the shapes are correctly distributed. Each particle uses the proper geometry from the shape list, just like in TypeFlow. Also keep in mind that in Bifrost, all instanced objects use the world origin as their pivot. So it's important to make sure your objects are positioned correctly in Maya, otherwise the instances might appear offset or misaligned. Now let's go a bit further and see how we can use attributes for shading, just like we did earlier. Start by adding a randomize geoproperty node before the create instances. This node will assign each point a random value between a minimum and maximum that you define. Give your new attribute a name. Here I'll call it random_1. You can inspect the values in the data browser. If needed, you can adjust the distribution using a curve, but in this case, I'll just leave it as is. Next, let's light the scene by adding a dome light, so we can preview everything in the render view. In the hypershade, you'll probably see 3 shading groups already present. Those are leftovers from 3ds Max. You can ignore them and create a new shader, then assign it to the Bifrost object. Add an iRamp RGB node and plug it into the shader's base color. Set its input type to custom and connect an AI custom data float node to it. In that node, just type the name of your attribute, random1. Each particle now receives a random color based on that value. You can easily tweak the ramp to control the overall look and color palette. The randomized geonode also includes a seed parameter. If you connect a Bifrost input node to the seed, it will expose it in the attribute editor, making it easier to adjust directly in the UI. You can add as many random attributes as you like. For example, here I'm adding another random value to drive the metalness of the shader. You can even isolate a specific shading node in the render view to see the result more clearly. Just select the node and click Isolate Selected in the Arnold render view. Now let's head back to 3ds Max and re-export the particles, this time including the age attribute. In Bifrost, replace the Alembic file. You should now see a new attribute named pointAge in the data browser. Like any other attribute, you can use it in shading, for instance, driving emission. course, don't use it raw. Normalize it, factor in maximum lifespan, or apply a remap to fine-tune the look. If you're interested, you can find a full demo scene with all of this already set up on my Gumroad. Also, the Create Instances node lets you switch to bounding box mode, which can make navigation much smoother in dense scenes. Alternatively, you can replace the output node with a terminal node, connect your instances to the final port, and for the proxy port you can connect something lighter, like a point scope. Then in the Bifrost attribute editor you can choose which port to use for viewport display and which for final rendering. And finally, since we've correctly exported the velocity attribute, motion blur should work out of the box. You can fine-tune its appearance using the velocity scale parameter. You can also use Bifrost to import regular Alembic meshes. Let's reuse the previous cloth example. In that case, we saved the velocity on map channel 5 and a random value on map channel 4. In the export particles operator, it's even simpler than before. You don't need to use the raw per vertex data field or convert the data to color. Bifrost is more permissive than Maya's Alembic importer. However, you do still need to convert the velocity coordinates, just like before, re-export the Alembic and import it into Bifrost. Make sure the FPS in Maya and the Alembic file matches the one used in 3ds Max. In our case, that's 25 FPS. Apply a shader to the Bifrost object and create a light to check it in the render view. The render looks mostly fine, though the normals could be smoothed. Use a soften harden edges node and adjust it as needed. Note that the mesh isn't very dense here, so the result won't be perfect, but it's good enough for demonstration. To retrieve the velocity, add a getGeoProperty node. Just like before, you need to merge the geometry before connecting it to other nodes. Then add a setPointVelocity node and also connect it to the mergeGeometry node. Use the getGeoProperty to retrieve the maxMapChannel5 attribute, which corresponds to velocity. By default, the node expects float data, but we are dealing with vectors, so we need to convert the type. Add a value node and set its type to vector array float3, then connect it to the setPointVelocity node. Finally, connect this setup to the output node. You may need to delete and recreate the output port to reflect the new data type. In the Arnold render settings for the Bifrost object, set the motion blur mode to velocity and enter the point velocity attribute. It should now work correctly. You can clean up your graph by adding backdrops and organizing nodes into compounds if desired. Now let's retrieve the random value stored in map channel 4. Use the same process as before, but this time with the maxMapChannel4 attribute. Add a setGeoProperty node and set its target to face component. Since this attribute is a vector and the node expects a float, extract the x component using a vector3 to scalar node. Again, you might need to delete and recreate the output port to see the updated attributes. Now you can use this random value in your shading, just like we did earlier in the tutorial. You can also get this Bifrost preset on my Gumroad if you'd like to skip the setup. Now let's look at how to export a simulation with multiple material IDs. In this example, the external faces have a material ID of 1, while the inner faces have a material ID of 2. This setup allows us to assign two different shaders in Max using a multi-sub object material. Unfortunately, Maya doesn't support multi-sub materials. Add an export particles operator and set the mode to Alembic mesh. We are exporting the entire simulation as a single collapsed mesh. Because the vertex count will change over time due to fracturing, we need to export velocity to support motion blur. Add a mapping operator, set its timing to continuous, and its mode to mapping by velocity. Choose a map channel and make sure to bake the mapping into the particle meshes. Duplicate this operator into the second event as well. Make sure to save the secondary mapping as UVW. It doesn't matter whether if it's a color or a vector, since we're using Bifrost. Don't forget to convert the velocity coordinates to match Maya's system. Now, in the Alembic compatibility settings, you should disable the option Material ID Face Sets in order to save the materials IDs as attributes instead of groups. But currently there is a small bug in Tyflow Exporter, and we can't see the material ID attribute in Bifrost or Houdini. So until this bug is fixed, the current workaround is to leave this option enabled, export the Alembic, and fix it in Houdini before importing into Maya. Import the Alembic into Houdini and make sure to set the same FPS as in 3ds Max. By default, the geometry will be packed, so you won't see any attributes. Unpack it to access the mesh and groups. Next, add a primitive wrangle to convert the groups into a readable material ID attribute. If a primitive is in the first group, give it a value of 1, and if it is in the second group, give it a value of 2. Back in Maya, import the Alembic into Bifrost. Again, verify that the FPS matches 3ds Max. First, retrieve the velocity just like before using getGeoProperty and a setPoint velocity so that motion blur works properly. Next, we want to separate inner and outer faces based on their material ID, so we can assign two different shaders. Add a getGeoProperty node and retrieve the mat ID attribute. Set the value type to array of 32-bit integers, not 64-bit. Add an equal node and set the comparison value to 1, which correspond to the external faces. Use a filter array node to filter the geometry using the output of the equal node. Add a delete faces node and use the filtered array as the input. This will remove the external faces. In the hypershade, create two materials. One for inner faces, one for outer faces. Import them into the Bifrost graph by middle dragging them from the hypershade. Then assign the first one to the inner faces using a set material nodes. Repeat the process for the external faces, this time filtering for value 2. It's very important to remove any material assigned to the Bifrost object, otherwise it will override the per face materials assigned inside the Bifrost graph. Now everything should work as expected. You'll see one shader applied to the inner faces and another on the outer faces, all driven by your original material IDs from Tyflow. An easier way to export particles with multiple shaders is by using USD. Start by adding an export particles operator and set the mode to objects. Personally, I prefer to export everything into a separate layer, just to keep the main scene clean, but that's entirely optional. In the export settings, make sure the preborn and deleted parameters are set so that objects scale to 0 when not visible. Also enable the limiter for minimum scale, which helps avoid issues during the export process. We can also add a mapping operator with a random value written into a map channel. We'll use this later in Maya to fine-tune our shading. You can now export your particles. Here I'm simply checking that the custom mapping has been correctly exported. Before exporting the USD, rename your shaders clearly. This will make them easier to work with later in Maya. Select all the exported particle objects and export them as a USD file. In the Vertex channel menu, make sure to include your custom mapping as a vector3 attribute. You can rename it if you want. Here I'll leave it like that. In Maya, open the USD layer editor and load your USD file. Again, make sure to set the same frame rate used in 3ds Max. In the outliner, when you expand the USD hierarchy, you'll see that each particle has been properly exported as a unique element. At the bottom, under the MTIL group, you'll find your imported materials. Let's fine-tune the external faces material. By default, the shader will be a USD preview surface. You can delete it. We are going to use Material X instead. In LookDevX, you'll find three shader families: Arnold, Material X, and USD. Currently, as far as I understand, they cannot be mixed together. You must choose one. Create a Material X standard surface node and connect it to the surface output. We are using Material X here because its ramp node is more intuitive and offers better color control. Add a Material X Primvar reader. If you remember, we saved the custom mapping under the attribute st4. You can verify this in the USD attribute editor. If you're missing the Bifrost USD menu in Maya, I'll link a guide in the description. It's easy to install. Set the Primvar reader type to vector3, then extract the X component and connect it to the coordinate inputs of the ramp node. Add a light and check your render. You should now see random black and white colors across the objects, driven by the custom attribute. You can tweak the ramp colors to customize the shading further. Since each object was exported as a unique node, motion blur should work automatically. You can also customize the shader for the inner phases, or apply any custom logic you like. Alright, I hope you found this tutorial useful. If you have any questions, feel free to leave a comment. I'll do my best to answer. Thanks for watching and have a great day.